So let's now take a look at the consequences of ideal mixing on the equilibrium between binary liquid and the gas above it. Okay, a binary liquid mixture. So imagine you have a mixture of two volatile liquids, A and B, and let's say the vapor pressure of pure A is 200 torr and the vapor pressure of pure B is 300 torr. That's an example. Okay, let's assume they form an ideal mixture. What would be the mole fraction of A in the vapor, and it would be in equilibrium with the liquid mixture, if the mole fraction of A in the liquid mixture is 0.6? Let's first answer that question. Let's see what happens. So you can say then the partial pressure of A in the vapor is going to be equal to its mole fraction. Oops, sorry. It's equal to its Rolle's law, right? So it's PA star times XA. So that's going to be equal to the pure vapor pressure of A is 200 torr. So let's treat these as exact numbers. And mole fraction of A is 0.600. So 200 times 0.6, that should be 120 torr. Okay. What would be the mole fraction of B in the vapor? Let's go ahead and do that calculation. The partial pressure of B in the vapor. It's going to be P star B times mole fraction of B. So again, this time our partial pressure of B, if it were pure, its vapor pressure is 300 torr. So we say B is more volatile than A. It's got a higher vapor pressure. So 300 torr times mole fraction of B. If A is 0.6, then mole fraction of B must be 0.4. Mole fractions add up to 1. So 300 times 0.4, that would be what? 120. So partial pressure of B is also 120 torr. Okay, so that would be, this would be the partial pressures of A and B. So how would you calculate the mole fraction of A in the vapor? Well, your vapor consists of A and B, right? So your total vapor pressure is equal to piece of A plus piece of B is equal to 240 torr. In fact, PA and PB have equal vapor pressures in this particular example. So you can calculate the mole fraction of each component in the vapor. So mole fraction of A in the vapor is equal to PA over P total. So it's going to be equal to 120 out of 240 torr. So it's going to be 0.5. Same thing, the mole fraction of B in the vapor is also going to be 0.500. Okay, so that's what you have in the vapor. Now what do you notice here? Mole fraction of A in the liquid. Okay, so in the liquid, okay, mole fraction of A in the liquid is 0.6. So let's go from 0 to 1 here. The corresponding mole fraction of A in the vapor is only 0.5. Okay, that's halfway there. Okay, so that's going to be, so the mole fraction of A in the liquid is 0.6. Its mole fraction in the vapor is 0.5. This is going to be Y sub A. What do you notice here? You say that the vapor, okay, is poorer in A, right? Similarly, what's the mole fraction of B in the liquid? Mole fraction of B in the liquid has to be 0.4, right? So 0.4 is the mole fraction of B. Oops. 0.4, that's the mole fraction of B in the liquid, and the mole fraction of B in the vapor is 0.5. So you say the vapor is richer in B. And that sort of makes sense because, look, B has a vapor pressure of 300 torr, pure B, whereas pure A has a vapor pressure of only 200 torr. So you say B is more volatile. You would expect the vapor that would be in equilibrium with your liquid mixture to be richer in the more volatile component. Okay, so the vapor is richer in the more volatile component. In this case, it's B. So what happens now if you made up a mixture so that the total mole fraction of A in the mixture, okay, is 0.53? How much gas would you have and how much liquid would you have? So let's say you have a container here. I mix A and B. Okay, some of the A's and B's will be in the vapor and some of the A and B will be in the liquid. How much of it will be in the vapor and how much of it will be in the liquid? Right? So let's say the total mole fraction. Let's just suppose that its mole fraction of A in the liquid is 0.6 and its mole fraction in the vapor is what we calculated to be 0.5. Okay. What in other words, this question is saying, what if we did this particular mixture and this is the situation that you got, that the mole fraction in the liquid is 0.6 from A and it's 0.5 in the vapor. Okay, but overall, for your total mixture, the mole fraction of A is in fact 0.53. So how would you solve this problem? Let's see. Think of it this way. Let N liquid be the total moles of A and B in the liquid, and N gas be the total moles of A and B in the gas. Okay? So that means, okay, mole fraction of A in the liquid times moles of the liquid. I'm just going to look at A, okay? Mole fraction of A in the liquid times the total moles in the liquid plus the mole fraction of A in the gas, so I'm writing that Y sub A, times the total moles of A and B in the gas, okay? That's the total moles of A. This is all the A in the liquid, and this is all the A in the gas. And what was the overall mole fraction of A? We say that must be equal to, okay, the overall mole fraction of A, Z sub A, times the total moles, which would be N liquid plus N gas. Okay? So that's the equation I have for A. And if that's the case, let me rearrange this equation to isolate N liquid on one side and N gas on the other side. Okay, so I'm going to put N liquid on the left side. So liquid here and liquid here. So I'm going to say moles of liquid times X sub A moles of liquid times X sub A minus moles of liquid times Z sub A, that's the overall mole fraction, okay, it's equal to, and then on the right side I'm going to have moles of gas times mole fraction of A in the gas, oops, I'm sorry, let me do it this way, and I'm going to move this one to the right. Okay. So I'm going to have moles. So I have Z sub A and gas. So mole fraction of A total times moles of gas minus mole fraction of A in the gas times moles of gas. Okay, so now what do we do? We factor out N liquid. We have X sub A minus Z sub A equals N gas times Z sub A minus Y sub A. Okay, and so now I can say N liquid over N gas is equal to, so now I can get the ratio of liquid, moles of liquid to moles of gas is equal to ZA minus YA over XA minus ZA. So I can get the ratio of the total moles in the liquid and total moles of the gas. Okay? Once I figure that out, let's see if that's a question. And that is, that's what I'm asking. That's what I'm asking for. Ratio of moles of A and B in the liquid to moles of A and B in the vapor. Okay, so that's how you would do your calculation. Now, if you know the total moles of A and B that you added, then you're going to say N liquid plus N gas would be N sub A total plus N sub B total. Then you'd be able to actually determine how many moles you have in the gas, how many moles you have in the liquid, and then using the mole fractions, you can say moles of A in the gas then would then be equal to what? Moles of A in the gas would just be Y sub A times N gas, okay, and moles of A in the liquid would be X sub A times N liquid. Okay, and the same thing for B, N sub B in the gas would be mole fraction of B in the gas times N gas, and moles of B in the liquid would be equal to mole fraction of B in the liquid times total moles of liquid. So you get all the information you need. Okay, so to recap, let's see what we got. You have the overall mole fraction of A, Z sub A is 0.530, so that is Z sub A. Okay, and the mole fraction of A in the liquid is 0.6. I'm going to put 0.6 over here. So mole fraction of A in the liquid, and the mole fraction of A in the vapor is 0.5. So I'm going to put 0.5 over here. Okay. So based on this, we say that moles of liquid times Z minus X, which is this one, 0.53 minus 0.6, so that's going to be 0.7, 0.07. 0.07, 0. Okay, so that's moles liquid times Z minus X must be equal to moles of gas times Y minus Z, which is going to be that one. So, okay, this is negative. We're doing that negative 0.7. And moles of gas times Y minus Z would be 0.030. And again, that's negative 0.030. Color code that. Negative 0.030. Notice that the negative will really just cancel out, so negative, negative. So you can just get rid of the negative sign. So you can get the ratio. What we're trying to do here, you're being asked for the moles, the ratio of moles of A in the liquid to moles of A and B in the liquid to moles of A and B in the vapor. So you want N liquid over N gas. So it's 0.070 over, it's 0.030 divided by 0.070. And that should give us 0.03 divided by 0.07 is 0.42, 0.429, 0.43. Okay. So that's going to be 0.43. Now, if you look at this thing right here, you can see that this equation right here is very similar to what you use in physics. If you remember your seesaw problem, if you imagine this was the fulcrum right here, you can say the moment arm, mass times distance from the fulcrum on one side equals mass times distance from the fulcrum on the other side. So this is known as the lever rule. Okay. So you can just use absolute values here for the differences in your mole fractions. It shouldn't really matter because if one's negative, the other one would also be negative. Okay. All right. Let's say you have an ideal liquid mixture of two liquids, ideal mixture of two liquids, A and B. Let's construct now what's called a binary liquid vapor phase diagram. A phase diagram, if you recall, is just a diagram that summarizes all the stable phases of a system under different conditions. Okay, so for a binary system, usually we can fix either pressure or temperature in order to draw a two-dimensional diagram. So in this particular case, let's say we're going to have a phase diagram at constant temperature. Okay, let's say at 298 K. Then what we do is to create this phase diagram, we create a plot that depends with the mole fraction shown on the x-axis. So we're going to go from x sub A equals 0 to x sub A equals 1. All right. Now let's see how we can construct this. What would be the total vapor pressure versus x sub A? Well, let's see. Partial pressure of A in the vapor is going to be equal to P star A times mole fraction of A. So what would this plot look like? Well, if mole fraction of A is 0, total pressure of A, partial pressure of A is 0, right? If mole fraction of A is 1, then your partial pressure of A is just its pure value. So it's going to be over here. This is going to be a straight line. Okay, so if you plot P sub A versus X sub A, you're going to get a straight line with a slope equal to P star A. And you should be able to easily show that that line is this line right here. Oops, let's fix that. So we're going to go from 0 to P star A. You can verify that the slope of this one is equal to PA star minus 0 over 1 minus 0, so that's just PA star. And you can see your y-intercept is 0. So y equals mx plus b, and your b is going to be 0. Now, similarly, if you did a plot for partial pressure of B, since you have an ideal mixture, okay, you can show that partial pressure of B equals P star B times XB, right? You can rewrite that as P star B times 1 minus XA, since small fractions add up. So that's P star B minus P star B x of A. Right? So when x of A is 0, what happens? If this is 0, then PB is just P star B. Let's just say it's over here. Okay. So that's P star B. And we're saying here that B is more volatile than A. That's a higher vapor pressure when pure. Okay. And so that's your y-intercept. Okay, so you can see this is your y. Y equals mx plus b, right? So your slope is negative P star B, and you should be able to show easily that that graph is going to be a straight line that's going to be sloping this way. Okay. Note that when x of A equals 1, what's your PB? X of A is 1. If this is 1, then you have PB star minus PB star. Your P sub D is going to be equal to 0. It's right here. Okay, so you can see your slope right here. For this black line would be rise, which is 0 minus P star B, divided by the run, which is 1 minus 0. That's just negative P star B. That's our slope right there. Okay, so if you add the two, you get the total pressure above the mixture. Okay. So we say that total pressure is equal to PA plus PB. Okay, and it should be easy to show that that's just this line right there. You have a straight line, and let's rewrite that. P star A XA plus P star B XB. So that's equal to P star A x of A plus P star B 1 minus x of A. Okay, all I did was replace that by 1 minus x of A. And I can combine these two. I have P star A XA plus P star B minus P star B XA. I'll combine these two and factor out x of A. I have x of A, P star A minus P star B plus P star B. And you'll notice here you have a variable equals a constant times another variable plus another constant. Okay, so this is your slope, and that's your y-intercept. So if you look at your graph, we can see that your y-intercept is P star B. That's your y-intercept right there for this line. P star B right here. Okay, and the slope of this line, is what? Rise over run, so P star A minus P star B divided by 1 minus 0. So your slope is just P star A minus P star B. Okay? Delta y over delta x, and you can see that's your slope, P star A minus P star B. Okay, so that's a plot of the total vapor pressure versus mole fraction of A. Now, what would be the plot of total vapor pressure versus mole fraction of A in the vapor? Remember, x of A is mole fraction of A in the liquid. Okay, let's start over. So we said, okay, from x of a equals 0 to 1, okay, our plot looks like this. This is P star B. This was P star A. And the graph's going to look like that. Now, of course, if you have, your graph could look that way if your A is more volatile. Okay, so it doesn't really matter. What matters is that you have a straight line, and then the value when x of A is 0 is P star B, and the value of the total pressure when x of A is 1 is P star A. Now, if we're going to plot the same total pressure versus mole fraction of A in the vapor, what do you think we'll find? Well, let's look at this one. We can see that B in this diagram, okay, we say that B is more volatile, right? Because P star B is higher than P star A. So we expect, okay, then vapor is richer in B than the corresponding liquid, and similarly you can say that it's poorer in A. So at that particular pressure, let's say this at this particular pressure right here, you would expect that the corresponding y sub A would be over here to the left. It's poorer in A. Remember, it's richer in A here. That way, right? So it's going to be poorer in A in the vapor. And so this is what you'll get. So if you did the calculation, you can do that here. And we did the sample calculation for this in the earlier slide. Okay? How do you calculate y sub A? If you recall, it's just going to be P star A. Oops, sorry, got it wrong. It's P star A XA over P star A XA plus P star, total pressure, right? P star B XB. Okay? And so that's what that graph is going to look like. So you can say that this is P star A XA over the total pressure. Okay? Let's see if we can create that graph using MathCAD. And let's just use some real numbers. Okay, so I need to do a graph, right, that plots versus mole fraction of A, the total pressure. Oops. Okay. So I have this graph, so I need to define my x of A. Oops. So I'm going to go from 0 to 1. Instead, I'm going to do it in steps of 0.01. So 0, comma, 0.01, the semicolon shows up as dot dot, and then up to 1. And I have to define what P of x of A is. P as a function of x of A equals P pure A. Okay, I can't do star with MathCAD, so pure A times mole fraction of A plus P pure B times 1 minus mole fraction of A. Right? Mole fraction of B is that. Okay, I have to define what P pure A and pure B are. So let's just say P pure A. Let's try 200. Okay, and let's just say P pure B equals, let's say, 300. And And there it is. And so here's your graph. I'm going to change this to graph from 0 to 400 so you can see it better. Oops. 0 to 400. Okay, so you can see right here in this graph, okay, this is 300 right here. That's your P star B. And this one right here is 200. That's your P star A. Okay? You can see that your slope is just PA star minus PP star. Now, what if I want to calculate? I can calculate my mole fraction in the vapor. I can say the mole fraction in the vapor is equal to P sub A in the vapor, which is P pure A times mole fraction of A divided by the P total. So the total pressure, P of X of A. Okay? Now I have to put this as a function of X of A because the mole fraction in the vapor depends on what the mole fraction is in the liquid. Okay? So what I've done here is this is partial pressure of A in the vapor over P total. Okay, so if I were to add that, I can plot this time partial total pressure, again same thing, but this time I'm going to plot it versus mole fraction of A in the vapor. And this is what I got. Okay, let's zoom in on this a little bit. It's going to be, let's go from 150 to 350. And there's your graph right there. Okay, so the red curve is total pressure versus X sub A. Okay, and then your blue curve right here is total pressure versus Y sub A. Right? So the way you would interpret this diagram is you're going to say for a given mole fraction of A, let's say X of A equals 0.5. This is the vapor pressure right here. Okay, this one right here. And so at this vapor pressure, you can see that mole fraction of B is Y sub A. Mole fraction of A in the vapor is this one right here. This is Y sub A corresponding to this X sub A. So you can see these 2 points on your diagram. Any 2 points, okay, on these 2 curves that correspond to the same pressure would represent composition of the liquid that's in equilibrium with the vapor. Okay, so it's the composition of the liquid. This is the composition of the vapor that's in equilibrium with that liquid. So this region right here in the middle, okay, any point in between these 2 curves would be what would be, okay, so that region between the 2 curves would be what you would call a two-phase region. Okay. If the overall composition of your mixture is somewhere within that region, it's going to split into 2 phases. On one side, you get the composition of the liquid phase. On the other side, you get the composition of the vapor phase. Right? So if you were to draw a line, a horizontal line through here, okay, this line connects the composition of the vapor and the liquid that are at equilibrium. You can refer to this as a tie line. Okay? So if the overall composition is anywhere on that line between those 2 points, it will split into 2 phases. One, the point that intersects the liquid line, okay, will give you the composition of the liquid, and the point that intersects the other curve would give you the composition of the vapor. Okay, how close you are to either curve will depend whether you have more vapor or more liquid at equilibrium. You remember the lever rule, right? So overall fraction of A, mole fraction of A minus X sub A times moles of liquid would be equal to mole fraction of Y minus overall mole fraction of A in the gas minus overall mole fraction of A times moles of gas would be equal. Those two would be equal. So that's your binary phase diagram for a liquid vapor mixture. So further interpretation of this, if you have the total pressure happens to be here, okay, let's say your total pressure happens to be down here, represented by this red dot right here, then let's say over here or here or here, any point on this region corresponds to a one-phase system. Okay, the pressure is too low for a liquid to form. What you'll end up here is just a gas. Okay, we say that this has a variance of C minus P plus 2. Okay, so the degrees of freedom here would be C minus P plus 2. This is a two-component system. There's one phase there, plus 2. And that gives you 3. Okay, 3 means to specify this system, you have to specify 3 things: temperature, pressure, and the mole fraction. You have to know if you see a sample of A and B, okay, and it's an ideal mixture, and you see that that sample is all gaseous, then to define that system, you have to tell me what's temperature, what's the pressure, and what's the mole. To be able to locate any of these points, you have to tell me what the temperature is, what the pressure is, and what the mole fraction is of one of the components. So I can do XA or XB. Okay, so the variance is 3. Now, similarly, above this curve right here, okay, at higher pressures, we also have a one-phase system. And in this case, you're going to have a liquid. Everything's a liquid. So if all you're seeing is a liquid and there's no vapor on top, that means you've squeezed it enough so there is no room for gas. Okay, so the pressure, very high pressures, your system's a one-phase system, and again, the variance of that system is going to be 3. What if you are in the two-phase region? If you're in the two-phase region, okay, if you're, let's say, right here in the two-phase region, between these two curves, you're in a two-phase region. Your variance is C minus P plus 2. 2 minus 2 phases plus 2. That gives you 2. Okay? What that means is you only need to specify 2 things. So temperature and pressure. If you specify the temperature and pressure, then you know what the composition of your mixture is. So if you specify that, remember this particular diagram, you specify the temperature. If I specify the pressure, okay, then I know precisely, I know automatically what the composition is of my liquid. It's this one, mole fraction of A in the liquid is this one, and what the composition is of my gas. So I only need 2 variables to define the system. Okay? So besides temperature, I can use pressure. Or if I know the temperature and I know the mole fraction of the liquid, of A in the liquid, then that's all I need to know, because from that I can calculate the total pressure and I can calculate the mole fraction of A in the vapor. Now, another type of liquid vapor phase diagram is actually a little bit more useful to us for practical purposes in the lab would be a boiling point diagram. A boiling point diagram is a diagram that usually you do this at 1 atmosphere pressure. So what pressure of 1 atmosphere, the normal boiling point, you can plot that versus mole fraction. So if you plot it versus mole fraction of A, from A, X sub A going from 0 to 1, when you have pure A, That means mole fraction of A is 1, right? Then the boiling point would might be something like this. So this is boiling point of pure A, okay? And when it's mole fraction of A is 0, then on this left side right here, you're going to have pure B. So the boiling point of your mixture is going to be T star B. So let's say B is more volatile, then it will boil at a lower temperature. Okay. So for mixtures of A and B, the boiling point is when the pressure reaches 1 atmosphere. Okay, so if you were to trace all of that experimental data, you might see something that looks like this. Okay. And let's see what happens here. What would be the boiling point versus the mole fraction of A in the vapor, if this was the case? Then you're going to say, okay, let's say this is the mole fraction of A in the liquid. This is what happens. A boils, right? Well, what do you think is the mole fraction of A in the vapor? A is less volatile, right? Oops, sorry, let me. A has higher boiling point, is less volatile. So your vapor is going to be what? It's going to be poorer in A, right? So the mole fraction of A in the vapor is going to be less than its mole fraction in the liquid. So the corresponding Y sub A, so if you can also draw a tie line here. So at this particular temperature, you might say, okay, the mole fraction of A in the vapor might be this one right here. Let me label that black. Corresponding to Y sub A. Okay. So generally, you'll get a curve, two curves that would look like that. Okay. So the interpretation here is at low temperature, everything's a liquid. Okay. At high temperature, you have a gas. So you have a one-phase region here, one-phase region here, and this region in between, right here, would be your two-phase region. And you got the same tie line. You have a tie line that connects points corresponding to the composition of the liquid and the vapor at equilibrium at the boiling point. Okay. A practical use of this is to predict what the composition is of a distillate. If you were to carry out a distillation, okay, this is T star B, A, small fraction of A, and let's say this is T star B. Oops, sorry about that. Okay. Let's say this is the mole fraction of A in the liquid. Okay, so when it vaporizes, okay, when it boils, okay, it reaches 1 atmosphere. The composition of the vapor, you'll notice, is poorer in A. It's going to be richer in B. Okay, so you can imagine then this process right here. You have enrichment in B in the vapor. Okay, so this is richer in B. And then what happens? This is your vapor, okay? Vapor is richer in B. What happens if you were to condense that vapor back to a liquid? Then the new liquid that you get, your distillate, will have this composition. So this is what you would call the composition of the first distillate. So this is your original XA. Let's call this XA first distillate. That's the same thing as Y sub A, right? And then if you were to boil that distillate again, okay, the vapor that you'll get will be even richer in B. So this right here would be the composition of the second distillate. And you can repeat that process. And in practical terms in the lab, what you'll do is you run your liquid, so you have through what's called a fractionating column. This is the principle behind fractional distillation. Okay, so you have your vapor, comes out here, okay, and then it condenses, it vaporizes, condense. So in a fractionating column, you have a series of vaporization and condensation, and as you go through that series of vaporization, condensation, what comes out of your column, if you have an infinitely long column, infinitely tall column, theoretically what comes out will be just pure B. Okay, so your volatile component comes out first, and then what's left behind, so this one, you'll have your flask right here, which you're going to be heating. But eventually what's left behind down here will just be pure A, and your pure B will come out of your distillation column. All right, so the phase diagrams we've seen so far are for the idea of case. Real phase diagrams based on real systems might actually look different from those, but to interpret these diagrams, the basic idea is this. If you're looking at a boiling point diagram, right, that's plotted versus mole fraction, let's say of component A, the way you interpret these diagrams is to always think about, well, what happens at high temperature? You would expect to see eventually at very high temperatures everything to be a gas. So the one phase region, which would be a gaseous, would be at the top of your diagram at high temperature. Okay, high T up here. And the bottom of your diagram would have to be, since it corresponds to a low temperature, would have to correspond to a one-phase liquid region. And the curves that you'd have in between, the curve at the bottom would have to be the boiling point. Okay. This is going to be versus the mole fraction or whatever it is you're doing on your x-axis, so mole fraction of A. And so the upper part of the curve would have to be this would be the composition of the distillate. So for example, if I were to say I have a mixture that the mole fraction of A is given by this much, then I'm going to say that mixture is going to boil at this temperature right here. Oops. Sorry. That mixture is going to boil at this temperature. I have to draw a horizontal line here. This temperature. Okay. And so at that temperature, when it boils, the composition of the distillate would have to be this one right here. So this is y sub A, and this is x sub A of the original mixture. Okay? So that's how you'd interpret that. So if you had a diagram that looks different from that, let's say you have something that looks like this. You have a water ethanol mixture, for example. Okay? Let's say I were to plot mole fraction of ethanol. Okay? So if I have 0 ethanol here, then I'll have pure water here, so it's going to be 100 degrees here, pure water. Now, ethanol is more volatile than water. It has a lower boiling point. I don't have that boiling point right now, so I'm just going to call that TB of ethanol, TB star. Okay. If you were to draw the experimental phase diagram for this, you might see something that looks like this. Okay. So again, the way you would interpret it is up here you have a one-phase system where everything's a gas. Down here you have a one-phase system where everything's a liquid. And so this curve, the bottom curve right here, okay, is going to be the boiling point of your mixture. Okay, that's your boiling point of the mixture. So if I have, for example, a mixture with the mole fraction, let's say this much of ethanol, then I know it's going to boil at this temperature. And this right here, the top curve would be the composition of the distillate. So if I were to draw a horizontal line tie line between these two curves. Where it hits the other curve, I go back down, I get the mole fraction of ethanol in the vapor. Okay? Now, if this was the mole fraction of the vapor, so my distillate will have this mole fraction. If I were to redistill this mixture, I'm going to get something even richer in ethanol, and then I condense it back to a liquid and vaporize it again. Eventually, I get to this point right here where I can continue distilling and vaporizing and condensing it, and it's not going to get any richer. Okay, so you've reached here what's called an azeotrope. Okay, so you have a constant boiling mixture here. This corresponds to actually what we solvent that we commonly encounter in the lab, which is 95% ethanol in water. Okay, so that's as pure an ethanol you can get by distillation from a mixture of water and ethanol. Okay, so if your ethanol water mixture is less than 95% ethanol, you keep distilling it, you run it through a fractionating column. The richest mixture that you can get in terms of ethanol would be 95% ethanol. That's the best you can get. By the way, just for clarification, this 95% ethanol here, this is by volume, okay? It's not mole fraction. It's not 95% mole fraction. All right, so anyway, if you had a mixture, okay, that is less than 95% ethanol in water, if you were to plot the temperature of the distillate that comes out of your fractionating column, okay, so you have a fractionating column here, so you get your gas goes to a series of distillations. If you were to monitor the temperature that comes out, eventually what you get at the very top, if you had an ideal column, that means an infinitely long column, what comes out at the top would be your azeotrope. So if you were to plot the temperature coming out at the top versus amount of distillate, then the temperature that comes out at the top would be the liquid that comes out of the top would be initially would be the temperature of the boiling point of the azeotrope. So this thing right here would be the boiling point of your azeotrope. Okay, and once you've gotten rid of all your azeotrope, what's left behind in your flask? So here you have your flask. What's left behind is just going to be pure water. Okay. So your residue in your flask will be pure water. So once all the azeotrope is gone, ideally, then your temperature, if you keep heating it, temperature is going to go up suddenly, and the boiling point is going to go up to 100 degrees Celsius. Okay, so 100 degrees Celsius right here. And that's what's going to happen to your temperature plot versus amount of distillate, where you're monitoring the temperature at the top of your fractionating column. Now, what happens if you have something that is richer than 95% ethanol? So let's say it's 99% ethanol. Well, it's going to boil right here, would be at this temperature, right? So higher than the azeotropic boiling point is your boiling point for your initial azeotrope. But then what happens? It's going to the distillate is going to be richer in water. Okay? Actually, it's richer in the azeotrope because you can't get water out of this one. It's going to be richer in water, and then you condense that distillate. You keep doing that. Eventually, it becomes what comes out of your fractionating column will just be the azeotrope, and what's going to be left behind in your flask will be pure ethanol. So the only way you can get pure ethanol by distillation then is if you have something that's already richer than 95% ethanol to begin with, and that ethanol is not what comes out of your distillation column. It's what's left in your flask. Okay, so if you were to make a plot of that, okay, then again, what comes out of your fractionating column would initially be your temperature of the liquid coming out at the top of your fractionating column will be the boiling point of your azeotrope, and then if you continue distilling what's left in the flask, which will now be pure ethanol, your boiling point will be whatever the boiling point is of pure ethanol. Okay, so if this black curve right here is what you would get if you have something that's already richer than 95% ethanol to begin with. Okay, of course, these are ideal plots, so in reality, you might get a curvature there, okay, and the same thing for the other plot for water, for the mixture that's less than 95% ethanol.